Okay, thanks very much. It's great to be here, and thanks especially to Charlie and Alan for inviting me to take part in this Summer Institute. Unfortunately, I couldn't come any earlier than today, but we already had a really nice discussion before coffee about risky decision making, and I'm really looking forward to the next couple of days. So the work I'm going to talk about takes an evolutionary perspective to decision making. I'm going to investigate in this talk how natural selection shapes decision-making rules in the kinds of complex and often uncertain environments that we find in the natural world. And I'm going to argue that when faced with this uncertainty, animals, including people, and so when I use the term animals in general throughout this talk, you should be thinking of people as part of that. Animals, when faced with this kind of uncertainty, might rely less than we think on sophisticated learning algorithms or kind of complex computations going on in the brain, and perhaps instead they might rely more on listening to what their body is telling them. So the work I'm going to talk about is truly collaborative. So it started while I was a member of the Modelling Animal Decisions group in Bristol. This was a group that was started as a result of Alistair Houston being awarded an advanced grant from the European Research Council, as part of which he was able to employ three of us as postdocs, so Andy Higginson, myself, and Pete Trimmer. Dave Mulpress is a PhD student, and also co-directing the project was John McNamara, his long-time collaborator. And the focus of this grant was to look at the evolution of the mechanisms that control behaviour. And although the group kind of disbanded when the money came to an end, all of us shown here have continued to pursue various lines of research still related to this topic. And in particular, some of the work I'm going to talk about towards the end is an ongoing collaboration that I have with Andy Higginson, who's also at the University of Exeter. So when Charlie and Alan invited me to take part in this Summer Institute, they posed two questions. And what I'm going to do is start out straight away by telling you my own personal answers to these questions, and then I'll spend the rest of the talk trying to substantiate those answers. So first of all, how do environmental properties shape the rationality of different decision-making strategies? Selection favours decision mechanisms that exploit the statistical structure of the environment, and I'm going to emphasise particularly the role of autocorrelation here, and use that to the organism's advantage. And in some situations, particularly situations that lack that kind of statistical structure, this can lead to seemingly irrational behaviour, and I'll give some particular examples of that. This is based on work that's a few years old now, done as part of the Modelling Animals Decisions group. The second question was, how do organisms adaptively learn which strategies to use in different environments? And I'm going to argue that explicit learning might not be necessary in many cases. And that's because physiological state variables provide valuable information about environmental conditions, and that allows organisms to make good decisions most of the time without necessarily having to do explicit learning. And this is more recent work that we've been doing, including some ongoing stuff, trying to get into the details of emotions and mood states. Okay, so I'm going to start off by saying a little bit about adaptation to complex environments, particularly autocorrelation, and the information that's contained in those environments and how individuals might learn from that. I'll give a specific example of how an adaptive rule that's adapted to these kind of complex environments can lead to apparently irrational behaviour. And then I'll explore some possible routes to understanding the underlying mechanisms of decision making. So thinking in particular about the psychological or physiological basis of decision making. And there are three possibilities I'll look at here. So first of all, decisions based on learning, then decisions based on energy reserves, And finally, I'll say a little bit, though it's very preliminary stuff, about decisions based on emotional state. So animals live in complex, variable environments where conditions often change stochastically over time. And because of that, an animal can't be sure exactly what conditions it's going to be exposed to in the near future, and therefore it can't be entirely sure what is the appropriate behavior to adopt. But although environments in the real world are often complex and stochastic and uncertain, they're not completely unpredictable. And that's because they tend to have this property of temporal autocorrelation. Now, all I mean by this is that conditions at one point in time are correlated with conditions in the near future. Okay, so for example, if it's raining today, it's more likely to be raining tomorrow than if it's sunny today. If food is very abundant this week, it's more likely to be abundant next week than if food was scarce this week. Okay? And basically, pretty much any feature of natural environments has this property of temporal autocorrelation at some scale. Okay? This is arguably a feature of all natural environments. And it has a very important implication. It means that current or past conditions then provide the animal not only with opportunities, but also with information about the future. And well-adapted organisms should exploit that information and use it to their advantage. Okay, so this is a fairly simple insight, but it has some important perspectives for us. So first of all, it can help us to understand under what conditions it pays to be sensitive to the environment at all. So under what kind of conditions should animals respond plastically to the conditions that they encounter? So there's been work on this looking at the conditions across populations, so what kind of environmental circumstances favour a population showing plasticity to the environmental conditions. This is from work by Carlos Botero and colleagues a few years ago. So they characterized environments in terms of two axes. So first of all, the time scale of fluctuations, how rapidly conditions are changing. And on the y-axis, the informativeness of cues, so the ability of cues to provide an indication of what the conditions might be like in the near future. So I just want you to zoom on into this kind of upper left part of the graph here, because their analysis showed that plasticity, so responding plastically to environmental conditions, depends on a combination of two things. First of all, you need to have an environment where conditions change rapidly, and that generates high uncertainty about the conditions. But secondly, you need to have some highly informative cues that reduce uncertainty about those conditions. Okay, so it's a general prediction about the types of environments in which we expect plasticity, including learning, to evolve. Typically, this has been applied kind of across populations. In some work with Willem Frankenhaus a couple of years ago, we pointed out that this same kind of principle can be applied within individuals as well. So if you look across the lifespan of an individual, you can use the same framework to make broad predictions about when individuals should be most susceptible to new information. Okay, and so it's the same basic idea here. Plasticity, including learning, is favoured at times in the lifespan when present or future conditions are highly uncertain. And the experiences that an individual has, which we can think of as the cues, are highly informative. They tell it what the conditions are going to be like in the near future, and that reduces the uncertainty. Okay, so again, we're dealing with that kind of upper left part of the graph here. And in general, if you look across the lifespan, uncertainty tends to decline as individuals gather more information about the conditions they're exposed to. So this is one reason, for example, why people tend to be more sensitive and susceptible to new information when they're young, and then as they grow older, they become more set in their ways. Okay, so those are just some general predictions, first of all, about the conditions under which we expect individuals to be sensitive to environmental conditions at all. But the other important implication of this property of autocorrelation is that evolved decision mechanisms that animals have should reflect this statistical structure, should reflect the structure of the environments in which they have evolved. And this can account for some otherwise puzzling phenomena, including so-called cognitive biases and cases of seemingly irrational behavior, a few of which are shown here. So these are all kind of well-studied features of human decision-making. A lot of work has been done on all of these different things. But actually, if we look across the animal kingdom, we find that there are analogous biases in lots of other animals as well. So just to give you a couple of examples, pet dogs show the placebo effect. So dogs, when they're separated from their owners, often show signs of separation anxiety. But if you condition a dog by giving it a sedative, such that it reduces its separation anxiety, then after being conditioned in that way, they will show exactly the same response to a completely inert vitamin pill. Okay, so they show exactly what we describe as a placebo effect. Another example is that honeybees, when they're shaken vigorously, become pessimistic in the sense that they will respond to an ambiguous stimulus as though it predicts punishment. Okay? So rather than these being kind of curious quirks of the human mind, there's good evidence that these kinds of biases or irrational features of decision-making are actually taxonomically very widespread, and that's exactly what we should expect if some of these represent adaptations to autocorrelated environments, which all animals will have been exposed to in their evolutionary history. Okay, so we shouldn't think of these as just kind of curious features of human decision-making. Okay, I'm going to go through in detail one particular example to illustrate this point of how a rule that's adapted to complex environments in the real world can produce seemingly irrational behavior in artificial situations. Yeah?
The question is, thank you. In the animal kingdom, as the animals become more sophisticated cognitively, do you also see that these biases tend to be more similar to humans as they go up the ladder?
That's a good question. And I don't know. I mean, what I can say is that many of these biases are really kind of deeply evolutionarily rooted in the sense that you find them in some very distantly related organisms. Intransitive choice, for example, has been demonstrated in slime molds as kind of amoebic organism that bears very little relation to humans in other ways. In terms of whether the biases become similar as you get kind of more human-like organisms, I think it's difficult to look at that because of the way that you can demonstrate these things. I mean, the phenomenon will inevitably show more similarity to the human type of bias just because of the type of context in which you might demonstrate it, because that organism is more similar to humans in all kinds of respects, phenotypically or ecologically in the kinds of circumstances it encounters. So I'm not sure you can really kind of disentangle it from just other general similarities to humans in that way. Does that answer your question? Yeah. Okay. So this particular example I'm going to go through is the phenomenon of contrast effects. Now, these are a pervasive feature of the psychology, the physiology, and the behavior of a range of organisms, including humans, and they're a striking illustration that we view the world around us in relative rather than absolute terms. The reason I put up this particular picture will become clear in a little while if you're puzzled about that. Okay, to humans, contrast effects are most familiar, I think, in the visual domain. And this example, this illustration here, depicts one famous example of a visual contrast effect. So the question here is, which of these two squares, A or B, is darker? So you put your hands up if you think square A is darker. Okay, a smattering of hands, okay. Hands up if you think square B is darker. No one's going to say that. Many of you may have seen this illusion before. In fact, they're exactly the same shade of grey. Okay, this is known as the checker shadow illusion. And the basis for this illusion is that when we evaluate the brightness of a particular square, we don't do so independently. Rather, we do so in the context of the surrounding visual information. Okay, so our judgment is context-dependent and relative rather than absolute. These kinds of effects are well known to researchers on consumer behavior. So, for example, the ratings people give to particular models of cars are strongly influenced by the other cars they're asked to rate at the same time. And this is something that's exploited by people in marketing and advertising. So again, our judgments there are context-dependent and relative rather than absolute. So those are both examples of what are known as simultaneous contrast effects. So the way you respond to a given stimulus it changes depending on other stimuli that are present at the same time. What I'm going to talk about here are successive contrast effects. So this is where the way an animal responds to current conditions is affected by conditions it's experienced in the recent past. So these are well studied in experimental psychology. Classic experimental paradigm for demonstrating this is a so-called runway test. Okay, so the experimental animal, in this case a lab rat, is trained to run along this runway to gain access to a food reward at the end. And you take the speed at which the animal approaches that food as a measure of its motivation for that reward. And you can adjust the size of the food reward to see how that affects the animal's motivation. So this classic experiment from Zeeman from the 1940s, he trained two groups of rats, one on a large food reward of 2.4 grams of cheese, another on a much smaller reward of 0.5 grams of cheese. And as you'd expect, the ones trained on the larger amount approach that reward much quicker. But an interesting thing happened then when he switched the reward amounts around. So in rats that were used to getting 2.4 grams of food and then were downshifted onto this smaller amount, they reduced their approach speed such that it was significantly below that of rats that had been used to getting the smaller amount all along, okay, shown by the dotted line. Okay, so that, at the time it was interpreted in terms of frustration or disappointment. These rats were used to getting a big reward, now they're getting much less, and they're not happy about that. In kind of modern terminology, we'd refer to that as a negative contrast effect. And equivalently, if you look at the other group, they're shifted up from the small amount to the large amount. They approach that larger amount significantly faster than rats that have been used to getting the large reward all along. Okay, which is interpreted in terms of elation, or what we'd call it as a positive contrast effect. Yeah.
Hi, so I'm just wondering what the pattern looked like as they were first introduced to the original chunks of cheese, because it seems like it might be some sort of change in behavior, and then like they overshoot and then readjust. So yeah, I could even see potentially a trend towards that in this data. So if you look at the beginning,
yeah.
how slow were these rats, or how fast were those rats when they first started the initial training?
I don't know for this data set. I would expect that those approach speeds would kind of gradually converge over time if you left them for long enough, as they kind of adjust to that being their norm. In terms of kind of what happens after the shift, if this graph was extended further, eventually the blue line will come down to meet the dotted line, the red line will go up to meet the dotted line. So there is an adjustment over time. What we're focusing on here really is just that sudden contrast when conditions change. But yeah, you're completely right, there are time-dependent changes regardless of that. Okay. Yes, so these are very kind of well-established effects. They've been shown in a wide range of organisms. vertebrates, invertebrates, they're, again, taxonomically widespread, and they occur in a wide range of different contexts. So, for example, in the context of mate choice and attractiveness, it's become known as the Fawcett effect. Nothing to do with me, unfortunately, so it's actually named after Farrah Fawcett, who was one of the actors and actresses in the original TV series of Charlie's Angels. So this comes from an infamous experiment by Doug Kenrick and Sarah Gutierrez in 1980. So what they did is that they showed a photo of a female student to a group of male university students, and they asked them to rate the attractiveness of that woman. And they did that before and after they'd watched an episode of Charlie's Angels, which was deemed to be this TV show in which it had very attractive female lead actresses in it. And what they found is that people gave a lower rating. They rated it as less attractive after they'd seen the episode of Charlie's Angels, whereas people who'd watched a different TV program, the kind of control group, showed no such change. Okay, so again, it's this kind of contrast effect that's suggested, but now in a kind of a more social decision-making domain. It's a bit of a kind of a crude experiment in a way, but there have been kind of more rigorous tests of this done since that original experiment that do support this general effect on attractiveness judgments. Okay, so that's just another example for you, but these are widespread across a range of different contexts. And they're curious if we're thinking in terms of rational decision-making, because they're a clear case where current behavior depends not only on current conditions, but also on past conditions, specifically whether those conditions in the past were better or worse than what they're getting now. And that's puzzling from a rational point of view, because it violates standard theories of rational behavior that say that your response should only depend on current conditions. After all, the returns that they're getting from their behavior, if you think about getting this food reward at the end of the tunnel, that's only affected by the current conditions. It's not at all affected by what they got in the past. They're not getting any different amount of food depending on what they had previously. But what we're interested in is why these effects would evolve. So they're very well established across a range of different contexts, but is there an adaptive basis here? Can we understand why these kinds of effects might make sense from an evolutionary point of view? And the key idea we had is that although these effects are irrational in the lab setting, the animal hasn't evolved in that lab setting. Okay? So it's evolved in a different type of environment, specifically one in which conditions change stochastically over time, and one in which that pattern of change may be uncertain. Okay? So what would a decision rule do that's adapted to those kind of conditions when you put it into the kind of conditions under which people test contrast effects? So in order to look at this, John McNamara, Alistair Houston, and I built a model looking at the evolutionary basis of successive contrast effects. So the key question here we're addressing is how hard should an animal work for food? This is an optimization model that we're using, and it's very much inspired by these kind of classic runway tests that I showed you earlier. So there's a single source of food available to the animal, and that's either rich or poor. The harder the animal works, so the more effort it puts in, the faster the rate at which it gains food. And it gains food at a faster rate for a given level of effort if the food source is rich. But there's a cost to this effort in that mortality is an accelerating function of effort. And that's to reflect the higher physiological costs or the higher predation risk associated with high levels of activity. So given these costs and benefits, we can then identify what's the optimal level of effort for an animal in this situation. Okay, and what we're taking here as the fitness currency is that the animal needs to maximize the total amount of food it gets before the end of its lifetime. If you do that, you can identify a particular optimum level of effort for the different conditions. It so happens that in this particular case, the optimal level of effort is higher under rich conditions than under poor conditions. Now, the specific thing that we added into this framework is that conditions could fluctuate over time. So sometimes conditions are rich, sometimes conditions are poor, and it just flips between those two states over time. But there are two possible worlds that the animal could be in. So either it's in what we call a good world, okay, where conditions are rich most of the time, and then briefly you get these periods where conditions are poor, or they're in a bad world, okay, so conditions are poor most of the time, and you get occasional brief periods where conditions are poor. The conditions in both cases are autocorrelated, so conditions tend to persist in the same state for a little while before they flip into the other state. The animal knows what the conditions are at the current time. It knows whether conditions are currently rich or currently poor, but it doesn't know when conditions are going to change, and crucially, it doesn't know which of these two worlds it's in. It doesn't know whether it's in the good world or the bad world. But the essential idea here is that by paying attention to the pattern of fluctuations between rich and poor conditions, that might give the animal information about which of these two worlds it's likely to be living in. Okay, so in our model, the animal starts with a certain belief, a prior, that the world is good, and that might be set by its evolutionary history, so the exposure to good and bad worlds in its ancestral populations, or it could be set by previous learning outside the particular experiment. We then assume that it continually updates its belief in a Bayesian manner, so we're using Bayesian updating here, and I'll say a little bit more about that later on. And then we want to identify a strategy that's optimal under these conditions. So the strategy is a level of effort given the current conditions, so whether conditions are rich or poor at the present time, and the animal's current belief that the world is good. We find the optimal strategy for that kind of stochastic, fluctuating world that I showed you earlier. This is the one that maximizes the expected total lifetime reward of the animal. But then once we've identified that optimal strategy, we take it out of that natural environment and we put it into one of these artificial test situations to see how it would behave in the kinds of experiments that are done to demonstrate contrast effects, where you suddenly switch the food reward. So I'll jump straight to the results then. So we've identified the optimal strategy. What I'm showing you here is how that strategy is predicted to behave under laboratory conditions that are used to demonstrate contrast effects. Okay, so initially, we have two groups of animals, both following this optimal strategy, that are exposed either to rich conditions or to poor conditions. And you can see their optimal efforts there. In this case, optimal effort is slightly higher under rich conditions. And then we upshift that group that were initially exposed to poor conditions. So we suddenly put them onto rich conditions, and we see exactly this positive contrast effect. Okay, this is predicted on the basis of our optimal strategy that's adapted to these autocorrelated environments. So it's now predicting a higher level of effort among those that were previously exposed to poor conditions than the group that have been experiencing rich conditions all along. And the reason that happens is because this initial exposure to poor conditions is giving the animal information. Okay, it's telling the animal that conditions are poor most of the time. Therefore, statistically, it's more likely that it's in the bad world than in the good world. And so when conditions become rich, they're probably not going to stay rich for very long. So the animal needs to capitalize on that opportunity, that brief opportunity, before poor conditions return. Okay, and that's the basis of that contrast effect. Equivalently with the other group, so if we take them, the ones that are used to getting rich conditions and then shift them onto poor, our model predicts a negative contrast effect. Okay, so a lower level of effort than those that were used to getting poor conditions all along. And again, the reason is that that initial exposure is giving the animal information. So in this case, it's telling the animal that conditions are rich most of the time, therefore it's probably in the good world, And therefore, when conditions suddenly become poor, they're not going to be poor for very long. So the animal can afford to just rest and hunker down and just wait for conditions to improve again. Okay, so although these effects are irrational in the lab setting, our model is suggesting that they could arise from an ecologically rational decision rule that's adapted to exploit an autocorrelated environment, okay, where current conditions give some information about the future. Yeah.
I was wondering if, so it takes them only 10 trials to understand where they are in the original poor condition. Why do you think...
Sorry, I should just point out, so these are not discrete trials, it's a time period, essentially.
Okay, so if it takes them 10 periods to understand or be primed into certain behaviors, depending on original poor, how do you explain why it takes them a lot longer to actually change their behavior again?
You mean the kind of gradual...
Yeah. Why wouldn't that be like only for 10 periods rather than 40?
So there's a gradual change which is due to them kind of learning about the environment. And that in that case, okay, the conditions have changed to poor. They're now gradually, the optimal level is going up because they're learning that actually it seems that poor conditions are persisting now. And so they're changing their belief from thinking they're in the good world to now thinking that they're in the bad world. So that's kind of and that's a slow, gradual process. But the very sharp drop is because conditions have changed. Okay, so that's not to do with any sudden change in information. That's about adopting the correct level of effort given the difference in conditions. So even if there was only one type of world, you'd still predict different levels of effort depending on whether conditions are rich or poor. Essentially because there's a different cost-benefit trade-off under those conditions. Yep.
So the rich and poor condition corresponds to the kind of food resource that's available?
Well, it's the rate at which they can gain food.
And how often does the rate change?
For this particular graph, I can't tell you off the top of my head. I mean, we can vary those parameters, essentially. And you see these contrast effects across a broad range of parameter space. So we can change independently how long rich conditions last for on average, and how long poor conditions last for on average, and we can change those independently in both the bad world and the good world. And these effects you kind of see across a wide range of parameter space, but I can't tell you what the specific values were for that graph.
Okay.
One somehow related question, is the extent to which the contrast effect appears somehow related to the amount of time that the subject has been exposed to a good word or a bad word?
Your question is, would the size of that drop be different if they were exposed for a shorter time?
Yeah, or a longer time.
Yes, it would. I think up to a point, right? So at some point it's going to asymptote. So if you think about their belief that the world is good changing, that can't go above 1 and it can't go below 0. So those will asymptote. When it gets to that point, you're not going to see much further change in the size of the contrast effect. But yeah, if you were to expose it for a little less time initially, then the size of that drop would be smaller. Yeah.
Okay, yeah. Me first. Maybe a brand new question, but are you going to talk about dopamine on this?
I'm not going to talk about dopamine.
So, okay. So if you look at this like from a reinforcement learning perspective, what you also see is prediction error. So like this level, what you show exactly scales the prediction error given that people learn. This also relates to Fiona's question, for example. So the more they already know beforehand, the stronger is, of course, they believe that they're in a good, not bad state. And
right.
Of course, there's theory on that dopamine encodes prediction errors. And then if you sum across dopamine, you get tonic dopamine, which actually is a predictor for how vigorously people respond. So maybe you're familiar with Yaniv's PhD work on that. And it's just like because we talk about physiological states, so this is like a natural process that tracks prediction error and that is determinative of how vigorously people respond.
Yeah.
So this is exactly what you see here, that this is not only model, but this is what you actually see also in humans even.
Yeah. So you see it on a physiological level as well, basically.
Yeah.
Yeah.
So you just average across prediction errors, and then the tonic level determines how vigorously people respond.
Yeah. Okay. Yeah. I mean, that's really interesting. Yeah. So I guess essentially what we're trying to do here is provide an evolutionary explanation for that kind of phenomenon, whether it's on a behavioural level or on a physiological level, with that kind of contrast effect. Yeah.
Since I'm also an animal and would like to know the relative terms, is there a relative? How is the negative contrast effect relative to the positive context effect?
So in our model, there is no asymmetry, essentially. So our model predicts that the negative contrast effects can be just as powerful as the positive contrast effects, and the other way around as well. So, and what it depends on, which of those two we predict to be stronger, depends on the precise pattern of environmental change. Okay, so varying the lengths of kind of rich and poor periods, you can generate situations where positive contrast effects are predicted to be really strong and negative contrast effects really weak, or the other way around if you tweak the parameters. So there's no basis in our model for predicting that negative contrast effects should be stronger, whereas I know in the empirical literature that generally seems to be the case. So what we aren't able to do here is provide an explanation why negative contrast effects appear to be stronger than positive contrast effects empirically. I mean, we can identify particular conditions under which we'd expect that to be the case, but I don't see strong empirical support for those particular conditions from what I've seen in the literature. I mean, I think that's genuinely a really interesting question. Why is it that negative contrast effects appear to be stronger than positive contrast effects? You know, there are lots of related phenomena as well, like loss aversion. Why is loss aversion such a powerful phenomenon? Why are loser effects in aggression much stronger than winner effects generally? And I think in all of those cases, we don't have a good evolutionary explanation for why that's the case. We don't really understand. It's a kind of enduring puzzle, but I think it's an interesting one.
And maybe related, rich and poor environments is defined towards a necessity level? Or?
No, so there's no kind of, well, in this model, there's no kind of starvation possibility, okay? So all the animal's trying to do is just get as much food as it can before it dies. And the richer the food, the quicker it can gain energy. So I know there are some evolutionary arguments suggesting that because of that lower starvation threshold, that might generate things like loss aversion, you know, this strong avoidance of really bad outcomes because that's going to end your life. Actually, there are lots of verbal arguments about that. If you do a formal evolutionary analysis of that, it's not really supported. So we have a paper with Dave Mulpress, who was on the first slide, looking at an evolutionary explanation for the fourfold pattern of risk preferences in prospect theory, and that kind of analyzes whether you should find these cases of loss aversion, and we don't find any support for it. So I'm always a little bit wary of those arguments talking about kind of a lower starvation threshold as being responsible for loss aversion. I don't think it gives a satisfactory explanation. Okay. So that was one example. So successive contrast effects. There are lots of other examples of decision rules adapted to kind of complex, potentially autocorrelated environments that can lead to seemingly irrational behavior, summarized in this diagram here, and they're also in the review article I gave as background reading. So if you're interested in any of those other cases, have a look at that. Okay, I now want to move on to talk a little bit about mechanism. So the work I've been talking about so far is very much at the behavioral level. There's a little bit about information state in the kind of Bayesian updating sense. But apart from that, I've not said anything really at all about the underlying psychological or physiological mechanisms that might be underpinning this behavior. As I said, a lot of these models kind of rely on Bayesian updating, so evolutionary models to look at decision-making under uncertainty. This is the kind of standard approach that you take Bayes' rule and you use that to update the animal's belief. So I guess most of you here are probably familiar with how this works, but I'll just quickly go over the details just so that we're all on the same page. So we're considering here the animal has some information state, what we might describe as a belief, and that can change in response to its particular experiences. And Bayes' rule gives us a logically consistent way to update belief about the state of the world in the light of new evidence. So new evidence being the cues that the animal receives. Okay, so this is the mathematical presentation of Bayes' rule. So what we have here is a posterior belief. So the animal has some probability that the environmental conditions are in state E, given that it's received some new piece of evidence, some cue about the state of the world. And that's related to its prior belief, so what it thought was the probability that environmental conditions were in state E before it received that cue. We multiply that by the probability that that cue would be perceived if the world really was in state E. So that's the likelihood of the cue. And then we divide by the overall probability of receiving that cue across all possible environmental states. That's the normalizing factor. Okay, so that's the mathematical formalism of Bayes' rule. That's how we use it in many of these models, including the contrast effect model for the animal to learn about what's the most likely state of the world. But is it really realistic to represent animal decision-making in this way? And there's been a lot of criticism of this kind of approach in the psychological literature in recent years. So these kinds of models have been accused of fundamentalism or telling just so stories. For example, Bowers and Davis suggested it was ridiculous to suggest that animals would behave in this way or that people would behave in this way. So this requires that they must store priors in the forms of probability distributions. They must compute estimates of likelihoods based on incoming data. They must multiply these probability functions, multiply priors and likelihoods for at least some alternative hypotheses. Surely that's not what we're doing when we're making decisions in the face of uncertainty. And these criticisms have been strongly countered by Griffiths and Hahn and various other people, pointing out that actually most Bayesian theorists don't really suggest that the decision maker is explicitly doing these things. And I think it's helpful here to bear in mind Mars levels of analysis. So really, most of these Bayesian models are focused at the computational level, so identifying what's the problem, how can it be solved, rather than really saying anything about the representation, the underlying algorithm, how information is processed explicitly, and how it's implemented in terms of the neural structures and pathways involved in decision-making. And actually, I think it's really nicely summed up by this paper from John McNamara and Alistair Houston. This is, in fact, the very first paper that John and Alistair wrote together back in 1980. And I still regularly return to it because it's full of real gems of insight. So they used this kind of Bayesian approach throughout a lot of their subsequent papers, but they made it very clear in this first paper. Our analysis says nothing about how an animal might achieve the optimal solution. It's possible, that, though unlikely, that the mechanism corresponds to the mathematical procedures outlined. It seems more plausible to assume that the animal has some simple rule of thumb. Okay, and that obviously chimes with a lot of the work that goes on here, thinking in terms of simple rules and heuristics for making decisions. And there are many contexts in which we can identify both kind of a theoretically optimal Bayesian solution to that problem and also some potentially simpler mechanism that might approximate that Bayesian solution. Okay, so I'll give you a couple of examples from social decision-making, which is more my area of expertise. So if you think in terms of aggressive behavior, So when should an animal escalate contests into physical fights? When it's uncertain about its relative fighting ability. Well, we can identify an evolutionarily stable strategy for doing that based on the Bayesian estimate. So the animal learns about its relative strength based on whether it's won or lost previous encounters. So that's a theoretically optimal strategy. But mechanistically, this is probably driven by winner and loser effects associated with underlying physiological changes that cause the level of aggression to increase after a victory, decrease after a loss, and so on. Or in the context of mate choice, okay, in an uncertain mating market, so you don't know what the distribution of available mates is like, you don't know what your own attractiveness is to them. Again, we can identify an evolutionarily stable strategy based on the Bayesian estimate that comes from previous encounters with potential mates. But we can also identify kind of simpler rules for adjusting this that might approximate that evolutionary stable strategy. So having a flexible acceptance threshold or some kind of aspiration level. So for example, from Peter Todd's work. So in both of these cases, right, we can have a theoretically optimal decision rule, but also a simpler mechanism that might approximate it. But can we go one step further than that? So can we be a little bit more explicit about the mechanisms involved? And if we can, how does the performance of those more mechanistic decision rules, how does that compare to the theoretically optimal Bayesian gold standard? And so this is the question that we've been trying to address in more recent work. So we decided to look at this question by starting with a very well-characterized problem. So this is a problem very commonly analyzed in models of animal behavior, looking at how an animal finds food when it's under the risk of predation. And the starting point for this work was a model published, in fact, the first paper that came out of the MAD group, led by Andy Higginson. So this is considering a situation where an animal has to choose how intensively to forage. Its foraging success increases with its level of activity, but at the same time, so does predation risk. So this leads to this trade-off between starvation and predation. This is a world where food items are discovered stochastically. Okay, so unlike in the contrast model that I showed you earlier, here the animal's just having stochastic discoveries of food items as it goes through the environment. And we have again here autocorrelation. So food availability is assumed to fluctuate over time. So again, we've got this fluctuation between rich and poor conditions. Now we can identify an optimal strategy if the animal knows whether conditions are rich or poor. Okay, so there are two kind of key features of this graph. The first is that foraging intensity should go up as your reserves get lower. So that's unsurprising. Obviously, there's a greater threat of starvation, so you need to forage more. But there's also a difference depending on whether conditions are currently rich or poor. Okay, so if conditions are poor, then you need to maintain a high level of foraging intensity up to a higher level of reserves because the threat of starvation is greater. Whereas when your reserves are high, you forage more under rich conditions because it's more profitable to do so. You get more bang for your buck. That's all well and good, but that's an omniscient strategy. Okay? That's a strategy that knows directly what the current environmental conditions are. It knows whether conditions are poor or rich. It has perfect information. But because the animal is stochastically discovering food items, it doesn't necessarily know that directly. Okay? Sometimes it discovers food items, sometimes perhaps it just has a run of bad luck and doesn't get anything. That doesn't necessarily mean that conditions are poor. So it's facing uncertainty, and the usual approach in these situations from an evolutionary modeler's point of view would be to use Bayesian updating. Okay, so it can have a Bayesian estimate that conditions are rich based on its previous success in finding food. But what we wondered is whether there are perhaps less cognitively demanding possibilities. And the thing we decided to focus on was the animal's energy reserves. So essentially, how much food is there in its gut? And the reason that this might be an important indicator is that obviously its reserves change depending on the foraging conditions. Okay, so this is an example trajectory of an animal foraging in this environment. The dotted line just shows survival of a population over time. And this is the mean reserve level. So when conditions are rich, obviously the reserve level goes up. When conditions are poor, drops down, rich goes up, poor goes down, rich goes up again, and so on. Okay, so on average, reserves are going up when conditions are rich, reserves are going down when conditions are poor. And in the long term, you can look at the distribution of reserve levels among a population of animals, both when conditions are poor and when conditions are rich. And you can see that those distributions don't overlap. Those distributions are not the same. So reserves tend to be higher when conditions are rich, as you'd expect. And that means that the estimated probability that conditions are rich should go up as your reserve level goes up. And so even if the animal doesn't directly monitor its experiences of finding food, perhaps it's completely ignorant of when it's found food and when it hasn't found food, its reserve level gives it an indication of the current food availability. So how well would a strategy just based on reserve level perform? So we looked at that by comparing the optimal performance of the omniscient forager, so the one that directly knows conditions, to the optimal performance under various types of information constraints. So first of all, a Bayesian forager. So this individual estimates the probability that conditions are rich from its recent foraging experiences. Then we've got this reserve-based estimate. So it estimates the probability that conditions are rich from its current reserve level. We also had a strategy that just adopts a single probability that conditions are rich, and that doesn't change over time. So this animal doesn't attempt to track changing conditions. It completely ignores autocorrelation in the environment. And finally, we have a pessimistic strategy. So this one just assumes that conditions are always poor. We also looked at an optimistic strategy that always assumes conditions are rich, but it died out very quickly, so I won't. I'm not going to present the results for that one. Okay, so just to summarize the differences in terms of information that is available to each of these different types of strategies. Okay, so they are all aware of their level of energy reserves. That's really important because if they're getting close to starvation, they need to start foraging quick. The fixed estimate strategy also knows the long-term frequency of rich and poor conditions. So on average, how much is the world in rich conditions as opposed to poor conditions? The reserve-based strategy also takes into account the long-term relationship between reserve level and conditions. Okay, so it's adapted to that statistical association between the richness of conditions and its reserve level. The Bayesian one also uses information from its own direct foraging experiences, and so it uses Bayes' rule to update that, and the omniscient strategy knows the environmental conditions directly. Okay, the optimal reserve-based strategy, how does it look, what does it do? So that's compared to this is the omniscient strategy that I showed you earlier. The reserve-based one shows a pattern like this. So it does something very similar to the omniscient strategy in poor conditions when its reserves are low. And that's because when its reserves are low, that probably indicates conditions are poor. So it should do something similar to the poor conditions there. When its reserves are very high, it does something similar to the rich the omniscient strategy in rich conditions, because a high reserve level indicates that conditions are rich, okay? And then in between, it's intermediate between rich and poor. So this is what you'd expect based on what it's doing. If we look at the distribution of energy reserves for all these different cases, just to show you that it does look similar to that schematic I put up before. So the distribution of energy reserves for individuals following these different rules is clearly different between poor conditions and rich conditions. But what I want you to notice here is that the distribution of reserve levels for the Bayesian strategy and the reserve-based strategy are very, very similar, okay? Both under poor conditions and under rich conditions. So it's already giving us an indication that they might have a relatively similar performance. But to really look at that, we need to examine the fitness of these strategies. So how well do they perform? So the measure we're taking here is how long do they survive? We're looking at the proportion of surviving individuals over a long time period, 2,000 time steps, relative to this omniscient strategy, which will always do best. So these are three graphs just for different sizes of food items. You don't need to worry too much about that. And in relation to the proportion of food that's concentrated in rich as opposed to poor conditions. So this is just to show really that the patterns are similar for a range of different parameter values. But the thing I want you to notice is that, first of all, the drop in survival is relatively small. Okay, so less than 1% in most cases. More importantly than that, if you look at the survival of the reserve-based compared to the Bayesian forager, it's actually not that much worse. So we have one strategy, the Bayesian, that's using all this information from each individual food discovery and putting it through this Bayesian algorithm to get an estimate of how likely it is that conditions are rich, versus a strategy that's just simply saying, how hungry am I at the moment? How much food is in my gut? Okay, and that latter strategy does almost as well. Okay, but the Bayesian strategy still does better. So now we need to think a little bit about the costs associated with those strategies. And this is where it becomes very difficult because we have no idea how potentially costly those different mechanisms might be. We don't even know where to start trying to measure something like that. Okay, so what we've done, this is the kind of closest we can get to that, is just by assigning some arbitrary survival cost, loosely based on what we consider to be the complexity of the mechanism. Okay, so we'll say that this fixed estimate strategy doesn't have any cost at all. The reserve-based strategy has some cost psi, and we'll say that the Bayesian learner is twice as costly as the reserve-based strategy, okay, to reflect this cognitive complexity. If we do that and then identify which strategy performs best, taking into account the costs of that strategy as well, this is what our model predicts. So this is for two different cost parameters, both relatively small. And what's plotted on the axes here are the duration of the different periods. So duration of poor periods, mean duration of rich periods. So that shows you kind of a wide range of the parameter space. What we find is, yes, the Bayesian learner, sorry, that should be a B, not an L. I've got to change that. The Bayesian learner does best in this region here. So that's where the duration of periods is kind of moderately long. But when conditions become longer, then the reserve-based strategy does best. Okay, so the advantage to the Bayesian strategy is so small that the costs outweigh that, and the reserve-based strategy does best. What's interesting as well is that actually this fixed strategy that just has a single fixed estimate of the probability that conditions are rich does pretty well, in fact does best when one type of condition is much more prevalent than the other. So when conditions are either generally poor or generally rich, then that fixed strategy does better, which was surprising to us. Okay, so to summarize those key findings, as expected, the omniscient strategy does best, then the Bayesian, then the reserve-based, then the fixed, then the pessimist. But the reserve-based strategy performs almost as well as the Bayesian under most conditions. And under most conditions, the difference in survival is less than 1%. The advantage of the Bayesian over the reserve-based is smallest when conditions change slowly. And that's because risk allocation is very important when conditions change slowly. So adjusting your foraging intensity depending on the conditions is very important when conditions last for a long time. But those are the situations under which your reserve level is actually a very reliable indicator of what conditions are like, because it has enough time to adjust to those conditions. The Bayesian and the reserve-based strategies perform least well when conditions fluctuate rapidly because their estimates become quickly outdated. And what we hadn't anticipated is that completely ignoring changes in food availability and just having this fixed estimate is surprisingly effective. For example, if conditions either fluctuate very rapidly or they're mostly in one state rather than the other. What all of this suggests to us is that the slight advantage of cognitively sophisticated learning mechanisms may not be sufficient to outweigh their presumably greater costs. Yeah.
Just a clarification here, and actually I might have said that, but I might have also missed it. The world is a Markov chain here?
Yeah.
Okay, and your Bayesian is also learning the transition probabilities?
The Bayesian, sorry, I should have said that, yeah. So all of the strategies are adapted to the transition probabilities.
Okay.
Okay, so you can consider them being aware of those transition probabilities. But what they don't know is when exactly it's going to change, but they know the probability.
So can you give me some intuition on how they adapt in terms of like stocking up on reserves when they as they learn that maybe transition probabilities are very high or very low? Because I'm missing that.
Sorry, you'll have to clarify. What do you want to know exactly?
Let's say that my intuition is that since it's Bayesian and it's learning the transition probabilities,
the Bayesian is not learning the transition probabilities. The Bayesian is learning whether conditions are currently rich or currently poor.
All right. So
it already knows the transition probabilities.
It already knows the transition probabilities?
Yeah.
Okay. So then can you...
So for example, if it decides to go out foraging,
yeah,
and it immediately finds a lot of food items, that's a good indication that conditions are rich as opposed to poor. Okay, so its estimate that conditions are rich will, the probability will go up.
All right, but if it knows the transition probabilities, then it should also be able to anticipate what state is going to be in the next period?
Yeah, I mean, yes, statistically it can, but
in this model it doesn't. Is that?
I mean, it doesn't know the conditions direct. So it knows, for example, it knows there's a probability of 0.2 that when conditions are rich, they're going to become poor in the next time step.
Okay. Yeah.
Okay. Yeah, but okay, it knows that probability, but then it gets to the next time step. Well, has that outcome actually materialized? Have we had one of those 20% outcomes where the conditions have changed, or has it remained in the same state, so the 80% outcome? And it doesn't know directly. So it has to continue sampling.
Sure.
Okay, well, maybe I'll
okay, sorry, yeah. If I haven't answered that properly, I'll clarify later, yeah.
I have two technical questions. So I guess I'll start with the most recent one. So you showed when the Bayesian system works better or worse than the reserve-based system based on this this cost parameter being twice as much for it versus the other. Have you found sort of a threshold cost ratio beyond which this relationship, so if you have a lower cost below a certain threshold, the reserve base might be better in all this region. If you have a higher cost above a certain threshold, the Bayesian might be better in all of this region, and there's a point at which they're equal, something like that.
Yeah, I mean, we haven't identified kind of specific thresholds as such because it depends very much on where you are in parameter space. But I mean, it behaves very much as you'd expect, right? So if you make the Bayesian one much more costly compared to the reserve-based one, then obviously the reserve-based one will start to spread out into the parameter space where previously there was the Bayesian one.
I mean, it could be interesting because clearly I suspect that 2 times was an arbitrary selection.
Yeah. Yeah.
And so my other question was going back to the first time you showed the behavior of an optimal, well, the optimal behavior. So isn't this whole thing like a dynamical system? Like the proportion of time you're going to forage is determined by your energy reserves, but your energy reserves are determined by how much you're foraging. So it's a continuously changing dynamical system. And
yep.
Is that built into your model?
Yeah, yeah. So the technical way we find the optimal strategy is through dynamic programming. So it's kind of recursive over many cycles.
I have a question about your reserve. So basically, this is kind of like the average of the past X rewards. How do you operationalize the reserve? It's the average above the past X reserves. So.
Yeah, so I didn't mention that. So each food item has a certain number of energy units to it. And there's actually a few different possibilities for that. So there's a distribution of sizes of items, really. That's done for technical reasons, really. But there's a metabolic cost. So if the animal goes out foraging, it uses more energy than if it rests.
So some kind of recency-weighted average value.
I suppose you might describe it in those terms, yeah.
Yeah. And then as a follow-up, I'm wondering, isn't that just very normal reinforcement learning what you're showing? So you have a very sluggish integration of the rewards that are coming in and you forget the very old rewards. Then of course it's clear that it's not so adaptive as a Bayesian updating model because it's very sluggish. You know, it can only learn very slow in this case.
Yeah. And so that's completely obvious. I think what's interesting here, though, is that it's actually not that much worse, right? So I mean, it will always be worse, but it was surprising across a large part of parameter space that just using the reserves in your gut does almost as well.
Yeah, and I was wondering, like, if you have a dynamic learning rate, for example, it might perform even better. So they can become really, really close to Bayesian updating.
A dynamic learning rate, in what sense?
So the learning rate increases if there's higher volatility, or if, like, or you have like a hierarchical model, so there's an inference on when change occurs, and the moment you increase learning rate, and then it slowly decays again.
For the Bayesian one?
No, for the reinforcement learning one.
Which is what? Which is the reserve-based one?
Yeah.
So we're not assuming any particular learning process from that.
Yeah, but basically that is a learning process. Your reserve is a learning process.
Yeah, but we're not defining how that learning process occurs, right? So you're saying we could introduce something else to make the learning more sophisticated, but we haven't constrained that, right? So the way it's learning, that's what's come out of the model, right? We're giving it the information. The information is, statistically, there's this distribution between reserve level and environmental conditions in the long term. There are, actually, think about it, there are more sophisticated things we could do. So as indicated in this graph here. So the information it's using is that, on average, conditions tend to be higher under rich. Reserves tend to be higher under rich conditions than under poor conditions. And so to make its decision, it's using its current level of reserves. What it could also do is take into account whether its reserves are going up or going down. So is it becoming more full, or is it becoming hungrier? And as you can see, there's a really strong relationship between conditions and the direction in which it's traveling. So yeah, I think you're right, that would enable it to do even better. And perhaps that's not very cognitively difficult either.
didn't try that with the
We
gradient?
haven't tried that, no. No.
Hello.
Hi.
Earlier in the program, we've had talks on exploration versus exploitation and foraging and so on. I'm interested in knowing, I'm trying in my mind to link what you said to some of those earlier insights. What do your results potentially tell us about human behavior, if anything?
So I guess there's a general message from this, which I'll kind of come on to in a little bit more detail in a minute, which is just that often when we're making adaptive decisions, we're not necessarily doing anything very cognitively sophisticated. And just using simple physiological indicators might be very effective in a wide range of situations. So I guess it kind of goes back to what I said at the very start, you know, that listening to what your body is telling you is that kind of gut instinct part. Essentially, we're providing some evolutionary hints about why having a gut instinct might help, might be effective in some situations. It's not just some kind of weird primitive urge. It's actually something that has an important adaptive functional value across animals, and I'm including humans in that.
So there's some human work, it's called average reward rate, where you look at reaction times and choice tasks, or the vigor people press a button, and you see that goes up with those reserve. So moments where there is a big reserve, which is indicative of a rich environment, people respond faster, potentially because opportunity costs of slow responding are higher. So you see that there's human research on those kind of processes.
I guess my slight discomfort is that obviously we all know that the human brain is far more capable cognitively than most animals. No. So how can we jump from the conventional animals to humans in that respect? That's what I'm thinking about.
Yeah, sure. I mean, we're clearly capable of Bayesian computations.
Yes.
We do it when we're running these models. I guess that's not my point. I guess it's more about you should use a mechanism that's efficient. Okay, and yes, an explicit Bayesian calculation might give you the most accurate answer, but is that justified by the extra costs involved? And what we're showing here is that probably not. No, at least for this kind of situation, there may be situations in which it is, but at least for this kind of situation, actually just paying attention to your physiological state is good enough. And so you shouldn't invest in a more expensive mechanism for doing that particular thing. But maybe you use it in other situations.
Right, thank you.
Okay. Okay. So, to summarize that part, the level of reserves provides a physiological summary of past foraging experiences, allowing the animal to perform almost as well as a Bayesian learner. And this is despite other strong constraints on reserve level. I think this is one of the particularly interesting things about looking at reserve level, in that it has a very important, a vital function for the animal besides its kind of ability to indicate current conditions, right? So there's a lower starvation limit. If reserves levels drops too low, the animal dies from starvation. There's an upper storage limit. The animal can only carry a certain amount of fat on its body. We also assume mass-dependent predation costs, and these are biologically very well empirically supported. So the heavier an animal, typically the more vulnerable it is to predation. At least that's the case in birds, right? If a bird is too fat, it can't take off and fly away from a predator quickly enough. Okay, so reserve level is actually a very strongly constrained physiological state variable, and yet we're finding that it can have an important information value that's very useful to the animal. And it doesn't have to be reserve level, right? So any physiological or psychological state variable could potentially function as a memory of past experiences. And unlike reserve level, many of those other physiological or psychological state variables might not be strongly constrained in that way. Okay, you can think of physiological or psychological state variables that the animal doesn't depend on for its survival. So perhaps those are useful as kind of information stores or physiological memories.
Can I ask a question?
Yeah.
How is that different from memory? Or isn't that what
Maybe it's not.
Isn't that what
Maybe it's
memory
not.
is,
So
right?
I guess I'm, you know. So I probably don't know enough about memory to be talking about that. But I guess what I'm trying to get away from is a very kind of brain-situated memory, very kind of, I hesitate to say the word cognitive, but that, you know, getting away from that and more a kind of a whole body physiological state. I'm thinking about things like hormones, essentially. More those kinds of physiological state variables that could potentially act as sources of information for the animal. And where this work is kind of leading us to now, and this is very kind of preliminary stuff, but it's thinking about the evolutionary origins of emotions and mood states. So things that often have a very kind of clear kind of physiological or psychological sensation. Could these be understood in similar kinds of terms? Have these arisen as kind of state variables for summarizing past experiences and acting as a physiological memory in some way? And we're not the first people to suggest this, so there's been a few recent papers looking from an evolutionary point of view at the origins of mood and emotions. So this work by Dan Nettle and Melissa Bateson, the adaptive function of mood is to integrate information about the recent state of the environment and current physical condition of the organism to fine-tune its decisions about the allocation of behavioural effort. That's very much in tune with the kinds of things that we've been looking at. So they had some kind of schematic models looking at how an animal responds to potential threats in its environment. So if an animal's foraging and it hears a snapping twig in the bushes close by, should it immediately run away or should it wait and gather more information? So this is looking at the kind of thresholds. It's a signal detection model looking at thresholds for detecting threat. And again, the importance of autocorrelation is key in their work. So if there's no autocorrelation, the level of threat today doesn't tell you anything about the level of threat tomorrow. You predict no dependence of this threshold. Whereas you predict a very strong relationship between threats yesterday and your optimal threat detection threshold today if you have an autocorrelated environment. Some other work as well. This is much more kind of computationally intensive simulation model work by Jarl Giske and colleagues. So they were looking at movements of fish through the water column at different times of day. And they set up this big computer simulation where there are a number of kind of perceptual inputs that feed into these neuronal responses and then undergo this developmental modulation, feed into these neurobiological states of hunger and fear. And the animal chooses between one of two, what they call a global organismic state. So either the fish decides it's hungry or it decides it's frightened. If it decides it's hungry, it will seek food and avoid crowds. If it decides it's frightened, it will seek crowds and avoid light. Okay, so they're trying to build models of behaviour that are based on this very detailed representation of emotional circuits. This does a pretty good job at predicting some of the patterns that they're interested in, so the change in the average depth of the fish over the course of the day, and things like if a group of predators suddenly appears close by, then you get this big spike in the number of individuals that are in this afraid state, and that also changes their movement patterns accordingly. I'm not going to say anything more about that because we're taking a kind of different approach with this in that we're trying to understand, kind of first principles if you like, how an emotional-based decision-making system would evolve and how it might constrain behaviour under certain conditions? Can it explain certain instances of apparently irrational decision making? We call this model the emotional stickleback because we've been very inspired by some of the classic ethological observations of stickleback fish by Nico Tinbergen. Now I think I'm going to have to switch out of this to the video. There we go. Okay, so this is a courting male stickleback. So he does this characteristic zigzag dance in front of the female. The female's right at the back there, not paying much attention at the moment. This is the male's nest down here, so he occasionally comes down to the nest. In stickleback, like many other fish, the male takes care of the eggs. So he's trying to attract the female down to his nest desperately. Right, so now she's watching him. It's a bit like she's watching a tennis match or something. In this model. Okay, but he's in this kind of courtship state. Oh, it's gone straight into the aggression. This is good. Okay, so also males aggressively defend their territory against other males because there's a strong risk that other males will eat their eggs. Okay, so males will invade another male's territory and eat the eggs. Obviously, that's a great threat to the male's fitness. And they're highly aggressive. They get really pumped up in these situations. What's interesting is that there it is. Okay. What was observed in these early experiments, and you can find a full video of this on YouTube. It's really nice. In these early experiments, they appeared to observe this kind of conflict between the male's emotional states. And sometimes he would be presented with a female, and yet he wasn't responding in the way you'd expect. So this is a male with bright breeding coloration, this red belly, bright blue eyes. There's a female there. She's a pregnant female. She's carrying all these eggs in her. He's really not interested. He's got his spines erect. And what you'll see is that he'll attack her a couple of times in a minute. So he'll lunge for her and bite her. There. So it's almost as if he's kind of primed for aggression and he's not responding to the female stimulus in that way. So we were interested in whether we could understand some of these kind of instances. Okay, can I switch back to the... Okay, so just to say, I'll just kind of quickly give you a couple of preliminary results on this coming out of our model. So we're building an emotional system in which there's kind of a valence between positive states for arousal and negative states for aggression. And the arousal axis is how intensely the male is showing that particular behavior. And we're looking at what kind of behaviors this will lead to. So a male, if he's presented with a male cue, although it's an error-prone cue, then his emotional state tends to move in the direction shown by the arrows there. So he gets to this kind of highly angry state, which will repel another male. Or if he receives a female cue, again, this is error-prone, the arrows will push his emotional state towards that kind of more amorous state in which he's courting the female. But we find a strong dependence on the previous emotional state. So if you look at his current emotional state and his emotional state in the next time step in relation to the particular cue that he's received, then there's this kind of emotional inertia in the system there, okay? I can go into that in more detail if anyone wants to know more at the end. This is ongoing work that we're doing at the moment. So just to conclude, animals have evolved in environments that are variable and stochastic, but that also carry information about the future due to spatiotemporal autocorrelation. Natural selection will have favored mechanisms that exploit the statistical structure. In unusual or artificial situations, such mechanisms can generate behavioral and cognitive outcomes that appear irrational, such as contrast effects. When conditions are uncertain, Bayes' rule provides a logical basis for making decisions, but it's unlikely that animals explicitly carry out Bayesian calculations. Instead, psychological or physiological state variables may act as a memory of recent experiences that guides decision-making, allowing a high level of performance. And this will have weakened selection for sophisticated learning mechanisms and may provide clues to the origins of emotions and mood states, and that's where our research is going at the moment. So just to thank the various people involved in this, particularly Andy Higginson, who I'm developing the emotional models with now, ERC and NERC for funding, and you guys as well for inviting me here. So thanks very much.